Godrays, those stunning beams of light that pierce through clouds, forests or windows, instantly elevating any scene to cinematic glory. But in game development, especially with Three.js, rendering true volumetric light is expensive. So we use clever fake techniques to get the same dramatic effect at a fraction of the performance cost. And in this video, we'll take this basic scene and turn it into this. Before starting, if you are new to 3D web development or want to build a solid foundation, consider exploring my course, React 3 Fiber, the ultimate guide to 3D web development, a project-based course with everything you need to know to start creating professional 3D web experiences with Three.js and React. Let's start by creating our project. To do this, we will use my starter pack available on GitHub. We are using the WebGPU one because we are going to use TSL for our shaders. You can find the link in the description, git clone, the URL and the folder you want to put it into, R3F Godrays. Once done, file, open folder, open it, and inside yarn or npm install and yarn dev to start the development server. Follow the link. We have a basic cube with orbit controls. Our project is ready. We have the code with our orbit control and our cube. Where do we go to create our Godrays? A video that really helped me to achieve this result is the fake Godrays to save a render time, which is a Blender tutorial. If we go with the final results, but you have all the step-by-step on how to achieve it. Some things are different in the Blender, but the way the nodes are creating the different shaders, the different materials, we just have to recreate it using Three.js. I could have started the video by just showing you step by step as if it was me that came with the full process. But I think it's important you know my process to learn so you can also learn to learn by yourself. Let's start by creating a Godray component. Inside components, Godray.jsx, and let's simply create a component, Godray. We will take some settings, we will define them later, and we will return a mesh. To be able to position it easily, we will add the rest of the props and pass it to the mesh. So if we pass position, scale, rotation, it will work out of the box. And the mesh we need for the Godray effect is a cylinder geometry, and the arguments to create it. To know the different parameters, you can check a Three.js documentation with the cylinder geometry, adjust and play with the different ones here, or thanks to the auto-completion and the typing, you can hover args and you will see its radius top, bottom, height, radial segments. It's an array of all those parameters. What we will need is a top radius, a bottom radius, the height of our cylinder, then the number of segments. We can hard code it, let's say 64, and 1 for the height. Then the next parameter after the height segment is open-ended. And what it does is we only want the side. So if we look, we added 64 segment like this, 1 height segment, we don't need more. And open-ended, it will remove the top and bottom faces, exactly what we need. For this parameter, we set it to true. We are good for the cylinder. We need to add a material, but first, let's define those variables. Let's say it's things we get from settings, top radius, bottom radius, and height, that we get from the settings. As we will add controls later, let's set a default value here. Top radius, let's use 1. Bottom radius, let's use 2. And height, 5. By the way, I'm not sure at how we pronounce height, and it is height. So from now on, I will try to pronounce it correctly. And for now, to display our mesh, let's add a mesh standard material with a color set to blue. Then inside experience, we replace the cube, the default mesh we had, with our Godray component. And because we're using a mesh standard material, we will need to add some light. We can use the environment with preset sunset. We'll get rid of that later. Or even simpler, let's use ambient light with a low intensity. Okay, if we reload, the camera is way too close. Let's use 0, 0, and 5, and maybe a much bigger field of view, 75, much better. And okay, we can see our cylinder. If we turn, it's like nothing is happening because the shape of the cylinder is always the same and we don't have any lighting showing any difference. Because ultimately Godrays are light, we will switch to a dark background to bring light on top of it. Here, let's switch to 333, a very dark black. Okay, we have our mesh structure to create our Godray. Now let's create the shader material that will represent those Godrays. To create our shader material, we will use Three shading language, TSL. I explain more about how it works in my tutorial named How to Create a Lenticular Material with TSL and WebGPU. Or you have 2 dedicated lessons in my course, WebGPU TSL and GPGPU Particles with TSL and WebGPU. To convert our mesh standard material into a node material to add nodes using TSL, we rename it mesh standard node material, so it will inherit from a standard material. But to be able to use it declaratively like this using React 3 Fiber, we need first to import mesh standard node material from Three/WebGPU, and then to extend it using React 3 Fiber using mesh standard node material. By doing this, it will make it available as a declarative component with lowercase for the JSX component, while the class was using an uppercase letter. And if you are using multiple mesh standard node material inside your project, do this extend in the app directly. All right, let's create our nodes. To do this, we get them from a use memo we will create to not recreate the nodes every time. That will almost never change. We will get access to the nodes. Our use memo will return different nodes. Let's try it simply with the color node. We use color from Three/TSL and we pass a color. Let's say pink. And now to apply our nodes onto our material, we remove here the hard-coded color and instead we pass all our nodes. So it will pass color node here. All right, now our cylinder is pink. The first thing we want to do is to add some noise to texture the light. As Three.js is not yet much documented, to find the different noise implementation, you can check the examples from Three.js. And on the bottom right, behind me, there is a button to have access to the code. From there, you can see the different implementations of noise. Let's create our noise. Const noise is equal to mx whirly noise float from Three/TSL. And what we pass are the UVs. So UV from TSL. And to display the noise, we will do a vec4 of, let's use 1, 1, 1 to display white and the noise as the alpha. The transparency of our material will depend on the noise. Don't forget to import vec4 from TSL nodes. And to be able to impact the opacity, we need to add transparent on our material. Now, if we check, you can see something is happening, but the effect is not very noticeable. Let's try to multiply the UV just to see the effect of the noise. And now you can see the noise. It's much better, but it's not exactly the effect we want to achieve. What we want is rays of light. To do that, we will create something we will call custom UV instead of this. Custom UV. It will be equal to the normal of the cylinder. We can get it with normal local. And to scale our noise, we will multiply it by something we will call noise scale. But as we want to pass it as a parameter here, we will call something named noise scale. Let's say we use 5 by default. If we want it to be reactive every time it changes, that it's updated in our component, we will use a uniform. So we create uniforms. Const uniforms, it will be equal to an object. Inside it, there will be our noise scale. It will be equal to uniform, the function of TSL, and our default value, noise scale. Now we want to use the uniform. We simply do uniforms.noise scale. Perfect. So the default value will be the default value here. And then to be able to update it, in the return of our use memo, we will return the uniforms. And then in a use effect, when one of the parameters of the uniform change, in our case it's the noise scale, we will add the other ones later, we will do uniforms.noiseScale.value is equal to noise scale. All right, here is what we have so far. You can see the very basic of the ray of light. Because we don't want our light to impact the ray of light, we won't display the color with the color node. So here it will be black, 0, 0, 0. And we will set the color as emissive node. And we will pass uniforms.color. So let's create our color uniform. Color, it will be a uniform of the color function. And let's name it Godray color. Okay, so again, we create our Godray color, or on the settings, we can just call it color. And let's use pink for now to have access to its color, but we name it Godray color. So we have access to Godray color here. And then use effect when Godray color change. Because it is a color, what we need to do is if we have a Godray color, uniforms.color.value.set, and then we pass the Godray color. Okay, here is what we have so far. We have our pink light. We can add a uniform to move the light effect over time. Let's create a time speed variable, 0.1. Again, time speed. In our use effect, if time speed change, we will change a uniform we will create later. Time speed with the right value. And now inside our nodes, we can code the logic for it. Uniform type speed. On our UVs, we will add the time, which is a TSL function that we multiply by our time speed uniform. So uniforms.time speed. Now you can see that the noise is moving very slowly, smoothly. Let's add an object behind to see the effect of it. Let's say a mesh box geometry with a white material. Here it is. We can see its ray of light on top of it, but the effect is not very convincing yet. What we will do is smooth the top and the bottom to make it more natural. Like if it's coming out a window or if it's coming out tree branches, the edges wouldn't be so harsh. Let's go into Godray. Let's add a smooth top of 0.1 and same for the bottom. We do the same principle as with the other parameters. We create our uniforms, smooth top, smooth bottom. Then in the use effect, we change it there, here too. And now we can create the node logic. Let's declare a smooth variable. It will be equal to smooth step. Use the one from Threejs/TSL because we need a node function. For the bottom, we will use 0 to the threshold we set, uniforms.smoothBottom. And to have a variable going from 0 to 1, we can use the Y UV, which are correct by default on a cylinder geometry. For this, UV from TSL.Y. And for the top, .mul and smooth step of 1.001 and our smooth top on the UV of Y. What it is doing is we have our UV going from 0 to 1, which is linear, what we had originally. And the smooth bottom will be like this. It will smoothly blend until the full value. And the other one will smoothly fade out to fine-tune the edges. Now let's use our smooth. Let's create alpha. It will be equal to our noise that we multiply by the smooth. And here, instead of directly using noise, now we correctly use alpha. And you can see that the edges are smooth, which is way more better. Now, to make it very convincing, what we want is to add some inverted Fresnel. What we want to achieve is to have the middle of where we are looking in any direction glowing while the edges are a bit fade out, like we did for the top and bottom, but this time it will be based on the camera position and position of the object. The Fresnel effect is doing exactly the opposite. The edges of the object are always bright, while the inside is not much lit. So we will do the inverse of this calculation to have the inside glowing and the edges fade away. To calculate the Fresnel, we need the view direction. We can get it from camera position, and we subtract the position world, and we normalize it. It gives us the view direction, where we are looking relative to the object. We need that to calculate our inverted Fresnel. And what it is the dot product of normal world with the view direction. We take the absolute value of it, and we can apply it to our alpha. So noise dot multiply by inverted Fresnel. Now it's subtle, but you can see on the edges, it slightly fade away. But to make it more visible, we can multiply it using the power, and not only a multiplication, of uniforms dot Fresnel power. As we did, we create our variables. Uniform of Fresnel power, here Fresnel power, and here Fresnel power 2. Let's use a default value of 5, and let's not forget to trigger it when it changes. Fresnel power, and here it is. By the way, for this use effect, I prefer to use one use effect and to reset all the uniforms than having a lot of use effect that will need to be processed by React every time. Now it looks much better. You can see the edges are very subtle and nice, while the middle is more bright. And if we move the camera, it's following nicely because our calculation is based on the camera position and the normal position of our Godrays. All right, now let's test it on a model that my fiance prepared for you. Models. You can drag and drop it from the final repository. You can preview it here in textured. And you can see that there is this room, and we imagine that there is a light going here, but it really needs Godray to make it much more immersive and realistic, believable. All right, let's add it inside our experience. We will simply load it using gltf, and the path to the model with source is equal to models/godray.glb. And I think a good default position is -1. All right, here is what we have, but the colors are a bit washed. A solution for it, if you go to up, is to use on the canvas flat. It will use no tone mapping instead of the filmic tone mapping. When we reload, you can see the color difference. It's much brighter. We can get rid here of the box geometry. And the final step is to add controls to position it correctly from the window to the statue. I will skip the part where I code the controls. Just get the final code or create your controls if you want to, but I don't think it's the most interesting part. So I will just paste it from my existing code. It's named Godray Builder. It takes the settings, and on change, it will retrigger an event. To connect our Godray to the Godray Builder, we have a few changes to do. By default, our settings will be empty, and instead we will use a use state to define the settings. This way, from the settings, we extract this, but we also have a set settings available for our Godray Builder. For our Godray Builder, we will need debug is equal to false to set it in the debug mode or not. And then in our component, if we are in debug mode, we will add the settings builder. It's a Godray builder. We pass the settings, and on change, it will call set settings. All right, now inside our experience, because we want to adjust our Godray, we use debug. All right, so now we have our basic implementation, nothing changed. We can adjust the parameters to find the best fit for this scene. But I forgot to connect position and rotation. So instead of taking it from the props, we will simply take it from the settings. It's new parameters we didn't handle before. Let's check if it works. Can we move it forward? Yes. Now we simply have to find the perfect combination of parameters. The most difficult part is to position it correctly and to scale it properly. I think I got something around 5 here and -6. Okay. Then we need to rotate it to go from the window to the statue. So it will be on the x-axis. You can rotate the camera to check if everything is placed correctly, even go outside. It's not a big deal if it goes a bit outside, but for now it's too short. Let's make it bigger, 14 dot something. So we have properly the red light on the statue. Now let's adjust a bit the rotation. I guess it's not enough, or too much, sorry, a bit less. And adjust the size, because we want it to be the size of the window, almost. Top radius, something like this. And bottom, we try to align it with the shadows. I think we are not far from something good. To adjust it properly, you can just disable smooth top and smooth bottom to see exactly where it stops. And once you are happy with it, you put them again. Adjust the noise scale if you want bigger ones or very smaller ones. I like small ones like this. It's moving a bit too fast, we can reduce it. Nice. You can play with the Fresnel power to see the impact. If you put it a lot, you only have it in the middle, while if you decrease it too much, it's not subtle anymore. Here, it looks okay. I think on the bottom, it's not smooth enough. So let's do it more. And the most important, because the color is a bit off compared to the rest of the object. If we choose something brownish, beige, okay. Much better, a bit darker, so it's more transparent and looks nice. Once you are happy with your configuration, you use the export settings, go to your experience, add settings, and simply paste. It will be in your clipboard. Then you save. If you have a nice code editor, it will format it properly. And now the final result is much more lovely. You can see the light on top of our statue, and from any angle, it works nicely. And if you want to implement a real Godrays where performance is not an issue, you can use the post-processing pass Godrays. It's an effect we are using in my Boyd's flocking simulation tutorial. You can see here the letters and the Godrays. Alright, once you are happy, you simply lock the camera so you don't go below or at weird position, and maybe add some camera animation, and you have a very nice scene. Thank you for watching, I hope you enjoyed this video. Please hit the like button to help this channel be more visible to other creative developers. Don't forget to subscribe to not miss my upcoming tutorials. If you want to continue your 3D web development journey, give a look to my course, link in the description below, or watch one of my other videos like this one, available here.